Okay. Uh, so as I mentioned last time, that this Friday we are going to have a quiz. I think one student emailed me. You right? Okay. I think we can arrange for one student. But my plan for today's class is actually just finish off a little bit from this chapter here, and probably I'm not sure if we have time, but if we have time at the end, maybe giving you another example for chapter 4. But if not, then just finishing this the equilibrium of beams. I think I need to give some context and another example as well. Okay, and make sure for the preparation for chapter 4 quiz, I think prepared from my exercise. I think it should be enough. I already giving you all the types of questions. Like if you have like the twist angle, okay, and you have torque. Either you start from the twist angle and then find the torque, or start from the torque and then find the twist angle. Okay, either way, and then there will be some different perspective or method. We call the basic force method and the displacement method. Basically, that is how we start. If you have torque and you want to know the angle, then you can start from there. Or if you want to start from reverse, okay, start from the torque and then find the displacement. You can choose between those two methods, the basic force method and displacement. Okay, but if I have time, maybe later we can have another discussion for the quiz. But for now, let's see this part here. We are having this supported beam. Okay. You'll see that either sides they giving you the fixed end. So the beams is having a length of L, right? And then it's giving some forces P. And then what else do we have? Okay, I think we can just go to the free body diagrams here, and you notice that although this fixed end, they are different. This is having a roller, and this is a supported fixed end. If you see the free body diagram, this part here for C is only having one line. It's not necessarily important within our case, because we are going to. So every time we dive into this chapter, we are mostly finding the relation between the shear stress and the moment, right? So usually the type of problems that might come for this case is usually the direction for the force is always transversal. So that's mostly the case within this. Okay, and I think all the type of questions that is going to be in transverse shear. If you include maybe non-transversal stress that may be affected, but it may complicate the subject, and then maybe need some another formulation. But let's say we are just focusing on the transversal shear stress, and then the moment. And then we can start from here, from this free body diagram, and then within this length. So we are given this A. Okay, so A can be any number, but A should be less than half L, okay, if you see from the proportions. And we are given the total length as L, right? And we can start from this 2 sigma moment just to get the force, okay, the transverse force. Okay, so we get the C and A for both this, and you can see that it's related to this value. Okay, every shear moment diagram is always start from this free body diagram, and then maybe finding some context. Okay, in our case here, the context is the shear force that is on the force on the diagram. Okay. And then later on, we need to evaluate what might happen, okay, within this diagram. Okay. So, what do we need this C and A? So the question here is basically just sketching the shear and moment diagrams. So basically, first we start from the shear, and then we start identify all the important elements. Okay. So important elements, including this distance, okay. Because why is important? Is A important? Because in this distance we have another force, right? That is perhaps in the system, the force that is taken will be changing, right? So the first one, we have this internal shear, which is given by the AY, okay? And then it's move and it change here, right? And then it's move again, and we have another internal shear here. So we made out shear and then the distance, and you need to be familiar with this. We can start by taking this subject, and my suggestion is to make the graph below the diagram. Okay, so take the graph here, and then take this as your graphs. So this will be our V. This is our, let's say, X, right? Let's just say X as our distance. And then we take notes on all the possible or important points. Like for example here, in point B, we get force, right? So we can make it out like that. And then from the our calculation here, we get our AY, which is this one. So that is AY, so we can write AY in terms on this diagram. So we can write here. So this is, let's say, the AY, right? Or we can write maybe here. Let me write on. So AY is equal P L minus A rel. Okay. Or maybe let me shift this a little bit to the top. Okay. Because I would like to draw the diagram. So at the moment here, from A to B, before getting the force P, we can assume that there is no change in the force. So let's make this force as it is. Okay. And then what will happen? And also, okay, maybe to help you get the idea of how we make sure that, okay, this is correct. All the forces, let's say we have forces that going down and going up. Let's just make that the one goes down with negative, okay, the one that goes up with positive. I think that will be helpful. So remember, in A and C, we get the force that is reacting to the forces from the top, right? So it's going up. So it's going up, so it's positive. Okay. Okay. And then from A goes to B, and in B it has P, force P. It goes down, right? So it goes down. How many points goes down? It's P. So we need to take this, and this distance is equal to P. Okay, so what will happen with this point? So this minus b. You get it? Okay, so let me draw first. Let me draw that this distance here is need to be p. Let me write with green. So this will be p. Okay. And I need to make this a little bit longer here. Okay. So P, PL over L minus PA over L, right? This is P. Minus P is equal PA, negative PA over L, right? So this one is the one that is going to be here. So this will be, this is negative PA over L, okay? And then we can make it goes through all this distance, okay? And then suddenly, so this is PA over L, right? And then I think our system is good because our CY is also PA over L. And I think this is just to prove that our diagram is correct, because all the value will be 0. Okay, because this is, I think we can also relate to statics, right? So this is going up and then become 0, right? Okay. So this is the area. This is the area. And you could also think that from this part here that is constant, you can think that the derivative of the v is 0. Right? You can think from that part as well. Okay. So I think this is shear diagram. Okay, shear diagram finished. Okay. And in the same way, I just extend this line to make the moment diagram. Okay, I think that is for x, and then this is for m. Or maybe let me write mx, and then this vx, just to note you that these are functions. Okay, and then remember that to get you the relations between the shear and the moment, I will write on the right side here just for some notes. Okay. So dv dx within this subject is 0, right? And then the d dx for the moment is a constant, which is described in v, right? So this is v, which is p L minus A over L. This is for, this is at distance A, right? Along distance A, we have the constant. And then at x equal A, we can use calculus techniques, just regular integral and derivatives. So MA minus 0, or M0, okay, let me just write 0, is equal integration from 0 to A of the Vx dx. This is equal, the Vx itself is PL minus A over L, and since it has dx, becomes x, so we just multiply with A basically. So this is PA L minus A over L. Okay, I think later you can just directly integrate. Okay, integrate just so if you know the functions, you can integrate. Like for example, if you know that this is a constant, then integrate is become just a linear function, okay? And then just plug in the distance. Okay, so we have this, our m at x equal A. Okay, so this is at x equal A, and then at nearby the L, so at the right side, so we can write A until L. So it's give the V is PA over L, right? Or negative PA over L. So this will be equal to, or maybe let me write a little bit left there so that I have space on the right side. So Vx is negative P A over L, which is another constant, right? Which we describe in the shear diagram. And then we take ML minus MA. This is just using the fundamental theorem of calculus, if you remember, the net theorem. Okay. So this is A, L, and we just change the functions into moment and the shear. So this is equal negative PA, it's negative PA over L, and then multiply with the distance L minus A. Okay, this is because it's just a linear equation, so it's not too complicated. And I think the worst case that might happen is, I think the most is the function will be just the parabola. So nothing more complicated than that. Okay. Okay. So what will we try to relate from the notes to our diagram? So let's just maybe let's continue this. Okay. This is the important points. Okay. Suppose so we have a constant, a linear, a constant for the slope. The slope is constant, which means that we are having linear, right? And I think you could, so if you already graph this, and this is just like plot like this, you can describe, this is positive, right? This axis here, right? This is positive slope, this is negative, okay? This is supposed to be set right? Okay, get it? And maybe sometimes it has some, maybe if this is like that, then you need to go to parabola, right? Okay, but the way you draw after some calculation or after some maybe you guess the graph, you can check whether it is correct or not. One way to check is you get compute everything, and you need to make it equal to 0. Like this one here, it's going to be 0, right? And you can do the same thing with the moment. So first is going up, maybe that way, and this is what? The PA, right? PA L minus A over L. So this is PA L minus A over L, okay? And then this will be the L, and then it's going down like that. And I think from our notes here, I think it's just, you can just conclude that since this is going to be 0, to put those two, then this will be correct. So it is correct that it's going to be 0 as we see from the calculations, right? Okay. So these are very basic parts on how we sketch the diagrams. Okay. So this is if you are given one concentrated force like this P. Okay. So what if there is no P but just another additional moment? So we take that, for example, here we have this, okay? So basically the same beam but changing the force with this moment at the same point P, right? So the same question, what will be the shear and moment diagram? So first, as usual, we take the free body diagram. And I think free body diagram is quite simple. Just take this, and then just taking this AY and CY, okay. And then we are going to have some moment here, M0. So this is A, B, and C. And then some distance here, A, and distance here is L minus A, practically the same component as we mentioned before, right? And then as usual, I think we can start writing here, taking the sigma moment, start from perspective A, and maybe just to make sure that we take the clockwise as a positive. So we start from the additional moment, external moment, the M0, negative M0, and then also negative CY, L minus A, this is equal to 0. And then we can describe the CY as negative MO over L minus A. This should be just L, sorry. M negative MO over L, right? And then another sigma moment on perspective C. In the same way, take negative positive on that clockwise, So ay multiplied with L, right? And then minus m0 is equal to 0. So ay is m0 and L. And I think we could see that these two components, their net is 0, right? There's the sum of these two forces are 0, and I think we could just start to write it down on the diagram based on the Cy and Ay. So first we could describe here, that is for V. So let's say this is V. And then let's say this is the X. Okay. This is X. So we start from Ay, which we have m0 over L, and let's just assume maybe over here that is the m0 over L. Okay. And then nothing happens within the shear force, right? So we just make it constant all the way through the C, right? And then it goes down how many? Negative m0 over L, right? And then it's back to the 0. So we have this shear diagram. Okay. Now the difference will be on the moment diagram, because we have an additional moment that needs to be accounted for when we compute the moment. Okay. So we have the constant, right? Constant slope, right? Positive, so it's supposed to be going up. But then at this B, it has additional moment that we need to count it here. Okay, so let's just take it into our diagram. Let's say that's our M. This is M, and then this is X. Okay. Oh, I forgot to write B. B is, let me just take lines from here, and then that's the point. And then the slope. So the slope, let me write here the notes, that from 0 to A, we can take the derivative of the M is equal to V, right? Which is equal to the Ay m0 over L. So this will be the slope. Okay. So this will be going up like that until here. Okay. And then we need to describe what is happening when x equal a. Okay. Oh, maybe before that, forgot to write the ma. So as usual, by calculus, we can take as x approaching to a, okay, from the left, okay, we can approach the a from the left, or maybe let me just write directly formula. So the calculus from 0 to a, this is taking the integrations from the v. So vx dx, because it's a constant, we just take the dx as x to the integrations. So this is going to be M O over L multiplied with A. Okay, so this will be the MA. This is MA describing from the left side of A, okay, from here. So this will be that M. Okay, so that is, this is equal to M O A over L. Now what is happening on x equal A? So let me just write here. At x equal A, we could say that, let me write first here, there will be a negative jump. Okay. And if we let the x getting into from the right side of the positive A, we could write that M A positive, this is equal the MA or MOA over L minus the MO, okay, the external moment, which in result, this is going to be, we can write MO A minus L, or to get the same form as previous one, let me write here is negative MO L minus A, okay, because L minus A is more describable. And then it's also giving us, let me write a little bit to the left, there. And then at the A to L, we get that this is also a constant, right? And then we can write with calculus is equal to from A to L Vx dx, right? And this will be equal to MO over L. This is L minus A, which gives you a conclusion that the ML will be 0 because of this. So this is the M on this side here. So this one is giving you the positive. So what should we write on the diagram? So we should write that the M is going down here. We have a negative jump. That is equal to negative MO L minus A over L. And then it goes up this much, okay? MOL, so it goes up here and this goes down. And then it goes up until L. And it should be the same slope as the first line. Okay. So this will be equaling to 0. So this will be the moment diagram. Okay, that's the moment diagram. Okay, just a two example. You have force, and then you have the moment. And I think another way to have typical problems here is if you have a distribution, and if you have distributions like loading, they will be also affecting the graph as well. Okay? So I think, yeah, I think that one is already quite complicated if you are not careful. Okay. Now, here, I already give the picture over here, but let me just write there and just focus first on how to get the. Okay. So this is the question. So determine the reactions and sketch the shear and moment diagrams. Okay. The beam is said to have an overhang BC. Overhang BC, it means that there is nothing here, okay, overhang. Okay. And then show all significant values, maxima, minima, position of maxima, minima. It means that what is the maximum force, maximum moment, okay. Now we have numbers, so we need to compute something. And I've given you the free body diagrams here. So this is already given. First is, if you have this kind of distributions, you can think this like a rectangle, okay, like a rectangle. So we can multiply the force like, you can think the force like y-axis, the height, and the distance x here is 4. So 4 by 8 is 32. So that is the resultant force, right? The resultant force. And where should we put? If you have rectangle, you should put at the middle, right? If it's triangle, it should be 1/3, 2/3, right? Proportions, right? Okay. So it's best to put here, the middle. So you have the concentrated force, 32 kilonewton from 2 meters from the left. Okay, this is the resultant. Okay. But what's the deal with this distribution loading? The deal is, usually, if we are just having one force like that, we just have the constant, right? We have constant. But if you have distribution loading, it's not constant. Maybe it has some linear type functions, right? So that's the difference. Okay, so we have this first reaction force for A, B, we have distance. Okay, I think we can have everything already. So we can start to draw. I think we can get the draw from here, just to get help from there, and then we can start to draw. So I think we can start from there. Okay, so this is V and X. We are in a meter. And kilonewton. Okay, before maybe we start from the statics part. So take the sum for the moment for A is equal to 0. Assume the clockwise positive. So we take 32 multiplied by 2, right? And then 16 by 6. And then by is minus by 4. Okay, we can continue after the break, okay? Okay, let's continue. So first, we get this, by, And then the next step is taking the moment for the other way around, the C, that is equal 0 to find the A. So we take that. So C will be 0, so then we start from AY multiply with 6, right? Oh, not C, sorry. Should be B, because that is the one that we are having reactions. So AY multiply with 4. And then what else? Minus 32 multiplied by 2. And then lastly is 16, right? 16 plus 16. And then 2. This is equal to 0. Okay, we can divide all with 4. So 4, 8, 4. So AY 16. So 8, right? So 8 kilonewton. So we can write in the diagram AY is equal to 8 kilonewton, BY is equal to 40 kilonewton. Okay. Okay. This is the diagram for the force and moment diagram. That is for our calculation only. Okay. But if you want to make the diagram for the shear and the moment, we went back to this original load diagram. We say this is basically a load diagram. Okay, just to help to notice. So this is load diagram. So usually you can have load and then shear and then moment. I think we need to put that here. Okay. Okay. Now first, only if you want to check whether 8 and 40 is correct, you can check back to the diagram. If they are equaling 0, then it's correct. Okay, so we move here. AY, we start from here, 8 kilonewton. It's positive, so it's starting from here. So we can imagine that maybe around this point here. 8 and yeah, maybe a little bit small, maybe around here. This is 8 kilonewton. Okay, start from there. And then what will happen with this distribution load? Okay. If you try to simplify, like for example, this distribution load, you can make it into resultant force, 32 kilonewton, and then you change this distribution load to the 32 kilonewton. It's not helping to draw the diagram, because the diagram needs to be elaborated when you have a distance, and you need to know what will happen in every distance. Okay? So we need to keep this distribution as it is. Okay? But to think that if you just make some logical sense from this 8 kilonewton per meter, to make this into just kilonewton, we need to multiply with the distance, right? So you can think this is a function. It's 8x, right? And x is depends on this distance, right? Which means that if we have this function 8x, what is the slope? But it goes down here. So we need to think that the function may be negative 8x. Okay? So let's say that's our function. So this function here, let me just write maybe phi x is negative 8x. Okay. Which means that we are going to have a slope negative 8. Okay, we have negative 8. I think you can just, as long as your diagram proportional, I think the slope can be in any way you want, but just mention that it's negative 8, slope negative 8. Okay. So maybe here, let me write that the slope, or maybe let me write here, at the V0, 8 kilonewton starting point, and then our dV dx is negative 8 kilonewton per meter. So we could start from this point, right? And then maybe makes this point B takes down, okay, to make sure that we are, and then point C also, just to give our locations where should we stop or where does something happen. So perhaps this is going through that direction, okay? So this slope is basically the distribution loading, okay? But what will be this this value for B? How much does this going down? Okay. Now remember, in B we have positive 40 kilonewton, right? 40 kilonewton. So we have 8 at the beginning, and it goes down with the slope of 8, right? And then you can think, like from this distance here, at B, this distribution loading is having 32 kilonewton, right? From 4 meter, right? From 4 meter it has 32 kilonewton, and then it has it has 40. So you could take that first. Maybe let's talk about the distribution first before the 40. So this is, you get further down about negative 32, right? After 4 meters. So let me write here. So after 4 meter, you get negative 32 kilonewton. Okay. So the total, negative 32 plus 8, it's negative 24. So this will be negative 24. Okay. This will be negative 24 because the distributions already reached the 4 meter at the B. Okay. So here, the number here is negative 24. And then we still at B. At B we have positive 40. So plus 40, so it goes up. So it goes up 40 kilonewton distance. So it goes up, let's say here, okay, here. I think that's better. So we say this part here, this is, we can say this is 40 kilonewton. So all the green color is just notes. Okay. So this will be 40 minus 24, which is 16. So this will be 16. So 16 kilonewton. Okay. And then what will happen? 16. We have 16. And at the end of the C, we have another 16, which means this is constant and then 0 and finish. We finish the shear diagram. Okay, so it's like, if you know, like if we already know all the essential numbers, what you need to do is you make a story. Okay, it's kind of like a story, right? You start from where, and at the end you need to make it into 0 because it's all in statically equilibrium, right? So start from here, and you need to determine which way he wants to go. And all the way here, it's basically confirmed by the load diagram, where the load is going through. It's going down or up. Or maybe there is there any moment, additional moment? Is there any distribution of loading? Okay. So we get the constant. Here, constant, and then goes down -16, right? And then it becomes 0. So here is the diagram. So this is shear diagram finish. But we still have one distance that we need to count within this. Let me just write this as xm. Or if you want to calculate xm, we can take that. Let me write here. So dv dx is -8, and phi 0 is 8. So at xm equal what? Then the phi equals 0. So phi equals 0 at xm equal 1, right? And hopefully the diagram, okay, you can, as long as you mention all the necessary number, okay, I think it should be okay. It will be also okay if you want to write down how we get the -24. For example, here we get -24 from this -52 plus 8, this will be -24. Or you could write from 8 minus 2 is -24, and then -24 plus 40 is 16, and then 16 minus 16 is 0. So I think we can write the whole function. It's not just 8x, but it's probably 8. I think it's better to write 8 minus 8x, right? Because 8 is the initial value. This is if you have only this loading, then you can think like -8x, but the whole function, we need to start from the very beginning here and start from 8. So v equals 0 when x equals 1, right? So we can say that this xm is 1 meter. And what is this 0 means? It's changing positive to negative. Okay, the slope is getting change from positive slope to negative if you integrate. So for the moment, we basically to integrate this, right? How we integrate? So we can think that this is positive, this is negative, and this is 0, and this will be the horizontal tangent. Okay? Okay. So let me write here. So at least calculus is useful. I heard so many students say that, oh, you won't learning calculus in the future, blah blah blah. But actually, if you learn the fundamental part, in every aspect of engineering, there will be calculus. Okay, so hopefully still remember, at least not remember all this, just remember the essential. Okay? Essential. Because if you forget the formula, you can just look, right? But not many people, when you look the formula, you understand, oh, I know this. Okay, because I also sometimes like forget some parts, but I know that how to explain, but sometimes I forget, so I would look the notes, and I think still okay, as long as we still understand, this should be okay. All right, now is maybe here. So this is the x, this is m. M is kilonewton meter. Okay. Maybe to, yeah, I think it's okay. It's okay. because it will be much more taking large part on the negative part, I think. Okay, now we take the, let's continue this line here and continue this part. And then we have another point that is important, which is the XM. Taking down, 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 down here. So we have positive slope, 1 meter. So positive slope means that we are getting this, right? And it's going to be parabola, right? Because it's line, and then we integrate, it's become parabola. Okay. You can imagine like if you think this is like negative x, if you integrate, you get negative half x squared, right? It's parabola. Which means you have the parabola that this goes like that, right? So it will be like that at this x equal 1. It's changed the slope and goes down. But it will be goes down until this part here. Let me make it a little bit down over there. So that will be perhaps like that. Okay. And this will be 1 meter. And then we can write something here. Let me make some notes here for M. So we take that the dm dx is Vx, right? And then slope going from positive 8, right? At x equals 0 to 0 at xm, right, equal 1. That's the first one. Second one, we can say the mx has local maximum. So local maximum at x equal 1, where the v is equal 0, or the slope is 0, right? Remember the calculus critical points and and that kind of things. And then we can write the m1 is, or minus m0 is equal to integrations from this Vx dx. I think if you want to skip this integral formula, you can skip and just using the geometric, I think still okay. This shape, the rectangle or triangle, I think it should be okay. Because this is supposed to be the area under the curve, and the curve that we might have is actually for sometimes for this kind of curve, we could directly go to this geometric shape. So this will be half. The Vx is what? The negative 8x, so half 8 kilonewton, and then 1 meter. So it's going to be 4. So what is 4? 4 is actually, we can just think from here. So 8, 1, and then divide by 2, just area of triangle. This area of triangle, and then this is another area of triangle, and an area of rectangle. That is our integrations for m. So if you want to calculate how much this is, we can take this triangle. So for example, here we have this part, right? So how much this the value for this m? M is integration from V. So integration from V is under the curve here. So this area, right? Okay. I think you can think like that. Okay, if you feel you write this, maybe you don't have any good memories of calculus, so I think you can just take the area. Just take the area. Okay, so 4 kilonewton meter. So right here, this is 4 kilonewton meter. Okay. And then from 1 to 4, so this is 4 meter, right? This is from 1 to 4. So this is the total is 4, right? Or maybe too many lines, not really good. Just get that one. So from 1 to 4, which is the blue vertical line, it's getting more negative, right? It's getting more negative part here. So it's getting around the negative parts. And then we can also write down that M4 minus M0 is and this will be typically, so from 0, so we say that 4, I think we can make it into because from 0 to 1 we already have 4, right? So I don't want to write that down again. So it's plus 1, 4. So this is 4 plus, this is going to be what? Negative 24 multiply with 5, right? Oh, 3 over 2. 3 over 2. What is the total? Oh, 3 meter. Okay. So 24 multiplied by 3 by divide by 2. Okay. So this will be half, negative 24, and then 3 meter, right? This is 3 from 4 minus 1. So this will be negative 36. Negative 36 plus 4 is negative 32 kilonewton meter. Okay. Or you think this is 4, okay, and then this is another one here is negative 24. Multiply the distance from this to here is 3, right? We multiply this is 72 divided by 2 is negative 36. So this part, the area is negative 36. Okay, so this one here should be negative 36, right? But we have 4 here, so negative 36 plus 4. So this here will be negative 32. Okay. Okay, as long as you get it, at least from the area, I hope it's easy to understand. Okay, I hope from this shape. Oh, I forgot the last one. So after this 4 meter, what's happened is we get into positive slope, right? So it's a constant, but here we need to get positive slope, so it's going up. Okay. And what is this? This is practically 16 multiplied with what? This is what? What is the distance? I forgot. Distance is 2. Okay, 2 is 32 kilonewton. right? So 32, negative 32, practically getting 0, okay? Okay. So that's our shear and moment diagram. Okay. So every time you may be perhaps confused on the relations, remember, okay, relations from that the uh, the d m dx is equal v. Okay, just keep in mind this relation. Okay, this is helping you out most of the time. If you are maybe not sure whether the graph is correct and how to start, you just remember that if you want to draw the moment, you can remember that the moment itself is integrate the result of integration of v, or we can also see from v that is v is the derivative of n. Okay? So you can see from this part here, we have slope, right? It's getting positive, 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 right? But it's a constant slope, which means we have, or we can say, or it's not constant. It's changing slope, but it's still positive slope, right? So we still have a positive on the upper side, but we don't know whether it goes up or down. But we have here that is changing from positive to negative. Negative here. So we can check from our line, and I think from all the case, it's matched up, right? It's matched up. Okay. From the derivative integrations, okay. Okay, there's actually one section in the textbook that is if the example on singularity functions or discontinuity functions, but I think I will skip that out. We are focusing on more other subject. So practically that is the equilibrium of the beams. Okay, maybe before we have more, this is actually the diagram that is provided. So is there any questions first? Have you tried the exercise for chapter 4? Not yet? Okay. I think we can have exercise, but let me check the question first. Okay, let me give some time first. Okay, let me check. Okay, let me put the exercise on this page. Let's try this one. This will be the last section on our course today. So it has the shaft, we have modulus, and then we have torsional loads on B and D. So D is here, the torsion goes there. B is here, torsion goes there. What else? Diameters all given. And then the question first is asking this torsion at D to make the rotation at C, where is C? Here. Oh, we have rotation here. To make that twisted angle equal 0. And then determine the maximum shear stress in each of the 3 rod segments. So we are having 1, 2, 3. Okay. And I think that is based on where the torque is, right? So this is the torque first. This is another one. So we have 1 segment, second, and the 3rd segment. Let me give you time to think. Okay, first, always try from the diagram, the free body diagram. Okay. You can start from this, and then or start from here because this is fixed on the wall. Or let's say just start from 3, I think it should be okay. Let's slice this. We have TV and you have well, you could, for internal one, you can maybe give the T3 to make it different from the one that is going to be here. So this is the torque here, is the external torque. Okay. So when you slice, you add some internal reaction or the internal torque. You could name as with any name you want. T1, T2, T3, or Tx, Ty, Tz. But I think T1, T2, T3 is much more sense. Make more sense. Okay, let me help to draw the free body diagram. Let me draw here, free body diagram. Start from, let's say, start from 3. So we have, this is TD. And then we have the reactions is, let's say, T3. So we say that T3 is equal to TD. And then we have, maybe too small, maybe make it bigger. And this is T3, and then this is number 2. Let's just make it a little bit small. Okay, so this is 3, this is 2. So we have TD going there. And then this is T2. Okay. And of course, from this second one, now T2 is equal to TD. Because there's nothing in between for the external torque, right? So you can just directly write S like that. Well, I think we can just copy this part. Paste here, and then add another one. So 2 maybe right there. And then 1 is here. Okay. Oh, this is D, this is D, C, this is D, C, E. And then another torque is here. This is TB. TB, which is 600, right? And then we need to have, because we don't know whether the T1 is positive or negative, we could just assume that perhaps it's going over there. But actually you can guess, okay, but anyway, with your assumptions, that should be okay if you're consistent. Okay. So we could write here that T1 or T1 plus TB is equal TD, or T1 is TD minus TB, or T1 is TD minus 600, right? 600 Newton meter. I think we can make it smaller. I think I'm making it too big here. Maybe making this smaller also. Okay, maybe after the free body diagram, another calculation that you might want to calculate first is the inertia. Okay. I think that will be better. So D1, D2 is the same, D3 is smaller, so we could write the inertia will be right here. Inertia for 1 and 2 is the same, right? Which is pi. I will write directly with the diameter. So D1 power of 4 divided by 32. 32 is came from, it's divided by 2 and we multiply by 2. So divide by 2 with power of, it should be 2 with power of 4 and then multiply with another 2. So D1 equal D2 is equal to 40. Let me check just to make sure that the number is correct. 40 power of 4 divided by 32 multiply with pi. Okay, 251,327, but I think well, let me just write first. This is going to be 251,327.4 millimeter for an IP3. The other one is 30. Okay, divided by 32. The other one is 79521.5. Okay, and then we can see the geometric deformations. So if we see from here, the geometric deformations. So if we have torque over here, and we have torque over here, so let's say that we are going to focus on the C, we can write the geometric available for this, for the let me write here, geometric of deformation, which means we want that the twist angle on C is 0. And the C, since this is fixed on A, then we could say that this is going to be considered by this angle 1 and 2. Now the angle, remember, the basic formula for the angle is T, L, and then G, and inertia. So we can write T1, L1, G is the same, right? So just G, and then inertia okay, and then plus T2, L2, G, and inertia 2, which is the same, right? And this is supposed to be 0, right? And T1 and T2 we could rewrite from this part here. So T1 is TD minus 600, T2 is TD. Okay, so let me write here. To change, T1 is 600, TD minus 600, sorry. And then L1 is 600. Let me write, the torque is Newton meter, right? So perhaps you need to convert to meter if you want. And then G is 80, so 80,000 Newton per millimeter squared. And then inertia is 2513227. And plus T2 is TD. So we are going to get the TD from these equations. L2 is 400. This is 80,000. And then multiply with 7. Okay. And then this is equal to 0. So first you get TD. Okay, if you want to calculate, you can change the millimeter to meter or changing the Newton meter to Newton millimeter. So I will change to meter, but I think I will just skip the process, but I hope you can calculate this. So TD is at the end is 360 Newton meter, okay, from these equations. Now because TD is 360, then T2 is 360, and T3 also 360, and T1 is 360 minus 600, which is negative 240 Newton meter. Okay, this negative is okay. You just to note that our direction is opposite directions. And then the maximum shear, we can write. So maximum shear or tau max. So tau max for 1, the segment 1 is T1 R1, right? Divided by the inertia. The same thing with the other segment. Okay, and then you can just calculate and you will get the answer. Okay. Okay, that's some other exercise. Please check the other exercise if you have time. Maybe different kind of problems. Okay, aside from this, maybe the power transmission. Okay, so see you on Friday and prepare for quiz.